Okay, good evening, everyone. Welcome, people here and people online as well. Welcome to the last lecture in this session, 23-24 session. Tonight we're going to have a double act. I'll resist any quip about a bog-off deal. But before we get into the main business of the evening, I'll do the usual update about the 5th edition of Geology of Scotland. In the background, we've been inquiring of the GeoSoc London whether they would be happy that we, Edinburgh GeoSoc and others, had a launch event for the 5th edition here in Edinburgh. Venue still to be decided, and all the details and everything still to be decided, when, what sort of format, and so on. But they're happy that we do that. And I'll have a discussion tomorrow with the editors of the volume to get our thoughts together and see what we might provide. So my question to you as a sample of people who are here, would the current audience, would you be interested in attending a couple of hours, late afternoon, early evening sort of event in June, perhaps, September, perhaps, to recognize the launch of the event, I hope meet some of the authors and so on and so forth. So would people generally be in favor of such an undertaking? Yes? Excellent. That's exactly what I wanted to hear. We'll use that as ammunition. Okay. So we're still on that theme of Geology of Scotland and the 5th edition. And on this occasion, we're going right to the later part of the book. And we're looking at 2 chapters tonight. It's maybe a little unfair on our speakers having to compress everything that they want to say into something of the order of half an hour each. But anyway, we'll take that risk, I think, with the interest of fitting things in. So Helen is going to speak first, and Helen led an author that, well, the title there is The Role of Geology in Developing Places. And that itself is intriguing, list of co-authors there. And then we'll move, hopefully reasonably seamlessly, into Colin McFadden, Nature Scott, talking about more the sort of geoconservation environment side of things that also features in its own chapter in the new volume. So Colin is the lead author for that chapter. So enough from me. I'll let Helen kick things off. Colin will come up afterwards, and then we'll do a unified question and answer session at the end. Okay, thank you.
Thanks very much, Graham. Great to be here. Can everyone hear me okay? Check that. Super. Okay. Yes, as Graham was saying, this chapter is towards the very end of the book. It represents a large body of work across a wide range of disciplines, and that's kind of which the co-authors and myself have tried to capture. So this is co-authored with people from Jackie Duckett and Donald Lynn from Glasgow City Council, Andrew Finlayson from the BGS, along with myself, Leo Peskett, who at the time was at Edinburgh University and now at Heriot-Watt, and Amy Bowker, who works at the Scottish Environment Protection Agency. So this chapter looks at the role of geology in developing places, as the title suggests. Geology has and continues to have a significant influence in how Scotland has developed. So it's underpinned the creation and the accessibility of natural resources, which in turn has informed where and when communities and settlements have developed. It shaped the physical appearance of the landscape, different rocks weathering in different ways and responding differently to the glaciations. And it's underpinned the diversity of our derived soils and the biodiversity within them. So all of these have shaped how Scotland has developed through time, and also how people link and connect across the country. So the distribution of farming and agriculture, where industrial development has happened, and indeed where we find vacant land in our modern day landscape. So as a result, geology not only has underpinned the natural environment and heritage, but it has also underpinned how Scotland has developed culturally and socially as a nation. So this chapter explores how geology provides not only a physical framework of natural resources and landscape, but actually how it underpins how culturally and socially we have evolved as a nation. And Geikie captured this, I think, really nicely in this phrase back in one of his works in 1882, where he said, probably few readers realize how, to a large extent, the events of history have been influenced by the geological structure of the ground whereon they have been enacted. So this theme sort of progresses through the chapter of the book and looks at examples of this. But firstly, I'd just like to get some thoughts and responses from you all as an audience as to what does the term or the word place mean to you? So if you just shout out, what's the first thing that comes into your head when you think of place? What do you think that means? Home? Local authority, yeah. There was another one down here which I didn't just pick up. Location, yeah. Birthplace. Belonging, interesting, okay, yeah. Yeah. Yeah, okay. Is there anyone online or not? Just shout out if you do, for a hand.
Sorry,
See?
there we go.
Anyone from the online group got any thoughts? No problem if not. No? No, that's fine.
He's got nothing to say, that man.
Yeah, so place is all of those things. Some of those things we're touching on a kind of spatial location point. Some of them we're talking about an association with a place, home, belonging, that type of thing, and politics. In Scottish planning policy, place is defined as the interaction between how places shape people and how people shape and inform places. So the term place was very deliberate in the title of this chapter in trying to capture that very dynamic interaction and interplay between geology and a physical location and then people back into that place. So yeah, so this chapter provides a series of examples as to how geology has influenced development of places in Scotland, both physically and socially, and how it continues to do so. So there's two main areas the chapter explores. One is the contribution of geology to the development of the Midland Valley through the Industrial Revolution and to the present day. And secondly, how geology can and is continuing to inform how we can develop climate resilience places as we look to the future. So I don't have time to cover all the detail and aspects that was done in the chapter, but hopefully this presentation gives a bit of a flavor. So looking first at the development of the Midland Valley. As you'll all know, Midland Valley is located in the central, more low-lying part, the central belt of Scotland, bounded to the north by the Highland Boundary Fault and to the south by the Southern Upland Fault. And the Carboniferous aged bedrock formed of repeating cycles of sandstones, mudstones, siltstones with coals and ironstones, seat earths within it, underlie a significant part of this Midland Valley in central Scotland. On top of that, there are superficial deposits of a variety of origins that overlay to varying thicknesses in different places on top of that bedrock geology. And these rocks, particularly the bedrock, have formed a really pivotal role in how the industrial revolution of this region and Scotland at the time and how population has developed in Scotland. So this is sort of captured quite nicely in this cartogram, which puts a different perspective on Scotland, looking at the proportion of the population by local authority area. And you can see there's an incredible distortion and bulge around central Scotland and the Midland Valley, which to a large part reflects that industrial development and population surge through the 18th, 19th and 20th century. And you can also see some other expansions there around Aberdeen from the oil and gas sector and so on. So what did this development of industry look like in the Midland Valley? This map here tries to depict the kind of significant extent of to which this mining underlays the Midland Valley region. So iron and steel production and the subsequent heavy engineering which they developed through the 18th and 19th century, largely due to the existence and accessibility of these geological resources in the Carboniferous bedrock. And at their peak, the Scottish coalfields collectively in the Midland Valley produced around 44 million tonnes annually. It was a big operation. And similarly, within the West Lothian oil shale formation, there was oil extraction and refinery, which peaked in the early 1900s, but that was producing 27.5 million barrels of crude oil. So these industries and the mining of the Carboniferous geology were for many decades the backbone of Scotland's economic development until as recently as the middle of the 20th century. The landscape and the geography, the places looked very different, as you can see in that top left image. And the jobs were different, the economy was different, but also socially there was development of culture and society around that time, the development of brass bands within the mining communities. And that today is still seen in those former mining areas and communities. That influence of geology and industrial development is still pervading that connection between people and location, i.e. place, today. So just to kind of give an example of the sort of scale of this growth and influence that it had, if we just look at Glasgow as an example, Glasgow had accessible resources from the Carboniferous bedrock of coal and ironstone, but it also had the River Clyde, which was a major transport corridor. And actually the River Clyde was progressively developed, deepened, dredged through the 19th century, but it also then connected into the expansion and development of the railway network at that time. So those two things combined led by the early 18th century, Glasgow as the third most important port in the UK, was a major place of import of tobacco, cotton, coffee, rum and sugar. By the middle of the 18th century, we saw the establishment of ironworks, which then led to an even increased demand on mining for the coal and the ironstone. And then by 1800, the population had grown to a point of 84,000, and Glasgow was a centre of heavy industry, renowned for shipbuilding, railway engineering, iron and steel manufacturing, and cotton spinning. So this kind of explosion of growth wasn't just seen in Glasgow, it was seen across the whole Midland Valley to varying degrees. And there were other examples that had the world's largest chromium works in Glasgow. It was a really significant development and expansion of growth. So geology has a fundamental role in the past development, but as I'm going to try and move on to show, it is still pervading how places in the Midland Valley continue to develop today. I really like this image, which shows the juxtaposition of a shale bing with the juxtaposition of the modern development and the housing. And hopefully by the end of this talk, there's a bit of a flavour of understanding for you all as to what's gone into putting those houses there and the considerations amongst them. So this industrial development and the geology has left a legacy of modified landscape. Today, it influences how we design buildings in Scotland, in the central belt, the location of where our new houses is built, the required remediation, and it's left an imprint on our broader environmental quality. So actually, our requirement for understanding the geology in today is actually sustained, if not growing, even though that industrial explosion has passed. And this is as we're trying to develop more compact, connected places and communities, which then can have lower emissions, greener transport mechanisms, etc. And all of that is looked at under the Scottish planning policy, but I'll kind of come on to that in more detail later on. So just to run through some examples. So all of this mining has left a network of underground void spaces. If you think back to that map, which I showed a few slides ago, which showed the extent of mining, just think in your minds, okay, all of that area is now potentially full of underground spaces. And a lot of the shallow mining in the Midland Valley was done by partial extraction methods, the main one being stoom and room mining, where the coal and resources were extracted in a grid-like pattern. So this now leaves the risk of collapse, subsidence, or crown hole development if there's movement, and depending on the depth of those workings, so how much strata is above them, and the coherence and dip of that strata overlying those void spaces. So the image on the left shows a surface expression of what it can look like if you have this crown hole collapse in a gridded pattern of these very shallow mine workings. This is in Broxburn near West Lothian. Equally, you may also see subsidence of buildings to the modern day, cracks developing in buildings dropping height or unevenly. So any development now, whether it's new housing or maintaining existing housing stock in the Central Belt, has to consider what is the risk of subsidence by putting an extra load on the surface. How coherent is that geological strata? How thick is it above some of these void spaces? And as a result of some of the effects of these, particularly in Glasgow, actually led to a really substantial programme of grouting works back in the mid to late 1980s. And it was really quite an extensive programme at the time. I don't know exactly the date that this photo was taken, but it was part of this grouting works. And you can see it's a street in Glasgow. There are several drilling rigs and grouting rigs down the street, simply injecting grout as angled holes down into the strata to try to fill that void space and stabilize any collapse or reduce the risk of it happening. So grout is typically comprised of pulverized fuel ash and cement, and it's injected at low pressure into the spaces, and then it expands and fills. So it's not very strong in itself, but what it does, it just fills those void spaces. Recently, there's been a move for more modern injection polymers and expanding grouts. So they're a foamed concrete or a polymer resin, and they actually, if the mine workings are very, very shallow, it's actually been seen that they can lift up a building by injecting them by a couple of millimeters. So subsidence is one aspect, mining subsidence. The other one is ground gas and mine gas, which I just want to touch very briefly on. So not only these void spaces exist, but they were quite often used as a storage space for some of the byproducts of the industrial waste, or even simply land gas. And these form potential sources of ground gas. So this could be methane, carbon dioxide, hydrogen sulfide. And if they come to the ground surface and accumulate in particular circumstances, it can pose human health risk. Mine gas specifically refers to methane, carbon dioxide, hydrogen sulfide, and carbon monoxide, which is released from the rock itself, from the coal seams and the surrounding bedrock. And this can happen if this changes in oxidization state of the rock, leading to the stored gases desorbing into the air or the groundwater within the bedrock. So that can be caused by movement of the ground or dewatering if the water table level changes in the rock. And these gases can be harmful if they migrate and make it to the ground surface and then accumulate in a space. So building design needs to consider this and ensure that there are either gas protection membranes and or enough ventilation built into housing design. These gases can be harmful to human health. That was demonstrable in the example of Gorebridge as recently as 2013. This is a picture of Gorebridge before some of the houses were demolished. In that the GPs in the area noticed that people were coming to them with a lot of similar symptoms, headaches and so on. And it was discovered that there was an accumulation of mine gases within the sumps of the houses because there wasn't enough ventilation. So very tangible impacts to modern day. Another impact of that former industrial development, utilization of the subsurface and the geology, is its expression and imprint on the geology and soil quality that we have. So mining ceased quite a long time ago, but it continues to be a big influence. So the groundwater quality in central Scotland in the Carboniferous bedrock aquifers is generally really very good, very potable. You could drill a borehole in your garden for your house supply, and it would be a reasonably good quality. But where it intercepts mine workings, there's often a problem of iron-rich waters. So they have elevated concentrations of bicarbonate, calcium, sulfate, iron and magnesium. So the sort of box plot at the very top here, this just shows the sulfate concentration in groundwater across the whole of the Carboniferous bedrock aquifers in Scotland, so across all of this sort of pale blue and pink. And you can see that the cohort which samples the groundwater intercepting mine workings has significantly an order of magnitude more sulfate concentration than in the other bedrock bodies, groundwater bodies. And these iron-rich mine waters are predominantly associated with the flooding of the deep mine workings, and the lowering of the water levels, which needed to happen during mining as they exploited deeper and deeper, meant that there was exposure of the bedrock to the air, a change in oxidization state, which then led to the sulfides, which are naturally held in the Carboniferous strata, to become oxidized and form ferric and ferrous sulfides. I just mentioned dewatering there. Dewatering stopped several decades ago now in Scotland, but that doesn't mean to say that they're not still seeing the effects of it. Rebound happens over many decades of that groundwater, of the water table, very, very quickly at first, and then more and more slowly as time goes on. But at Polkemmet Colliery in West Lothian, groundwater rebound was estimated to be occurring at still 10 meters a year, some 10 years after the dewatering had stopped. So the legacy and impact of that is very significant. And now when we're looking at building wholly new towns and new settlements in some parts of the outskirts of Edinburgh to the west and to the east, some of these things need to be considered, because this dewatering and rebound is still happening. These changes in oxidization and changes in groundwater quality are still happening. These void spaces are still present. So all of these things need to be thought of. And then finally, the imprint on soil quality. So this was from a systematic BGS geochemical survey, which was not just in the Clyde catchment as shown on this figure, but broader than that. But what it showed was that median chromium concentrations in Glasgow were higher than in many other cities. And that was inferred to be due to the presence of the volcanic bedrock in the area, but also the history of the chromite metal ore processing in the city, which once was the largest in the world and made ground. And several other sort of elements and chemical substances are elevated as well, but as you would expect in urban areas. So this figure here shows the chromium, and the red coincides with the sort of hotspots, elevated concentrations, the blue, the lower. And you can see there is a direct spatial correlation in a lot of places between where these elevated hotspots are and where these former chromium works were placed. And then this just sort of shows a comparison to how generally across the Midland Valley, but also elsewhere in the UK, how you have this imprint of human influence in urban areas on soil quality. So the grey bars are from urban areas, the white bars are from rural areas. And you can see that for all elements and in all cases, urban areas have higher concentrations of these because of the anthropogenic influence than what rural areas do. So in Glasgow and elsewhere, efforts to remediate this chromite ore processing residue has been extensive. It's been a huge amount of work in particular areas over recent years. So it can include diverting water courses away from these sites where the waste is held, in situ chemical treatment, capping, etc. And today, it's much more controlled, monitored, regulated by a comprehensive collection of legislation in Scotland, including controlled activities, environmental liability regulations, pollution prevention control regulations, and the contaminated land regime, which is part of the EU framework as well. And the contaminated land regime uses the suitable for use approach. So recognizing that risks from contamination are site specific and depend greatly on the proposed usage of sites, as well as many other factors. So it's not that you need to do a complete remediation in all cases. It can be tailored according to the site. So coming back to Glasgow, which I previously used as a case study of how the geology which underlay Glasgow had really informed the industrial development and societal culture of that place. Coming back to Glasgow as an example today. Sorry. Yeah. Coming back to how Glasgow today, all of these things, underground void spaces, gassing regime, soil and groundwater quality, are affecting how land and space is used in the city today. And vacant and derelict land is a key issue. It means all of that legacy of that industrial past and the geology means that almost a third of the Scottish population today, not just in the central belt, lives within 500 meters of a derelict site. Okay, so that a derelict site is a site which isn't used, but it's been used previously. Often they look a bit like a wasteland or not particularly appealing visually. And in deprived communities, that figure increases to over half. So across Scotland, we have just over 11,000 hectares of vacant and derelict land. And that really affects how people and society connect with places, because you have swathes of vacant and derelict land in between other housing areas and communities, leading to disconnects in how society and people connect across the city or indeed across the central belt. So bringing this land back into use, developing more connected, compact places is a cornerstone of planning policy in Scotland at the minute. But it is complex and it requires significant investment and technical expertise. So to give you an idea of this, Sight Hill, coming back to Glasgow as an example, Sight Hill in Glasgow is one of the largest brownfield development projects happening in the UK at the minute. It's about 50 hectares. It will provide 1,000 new homes, a new park, education centre, school, businesses, and a local community centre. And there's also, which I think is captured in this slide, a kind of pedestrian green transport bridge over the motorway, trying to connect this part of the city better with the inner city centre. But the redevelopment cost is currently at 250 million, with the required remediation work and also building the new housing and infrastructure. And several phases of ground investigation were required. Even just in one phase of that, it required about 1 million cubic meters of soil material to be moved to manage the amount of remediation needed at the site as a result of the residual waste chemicals and hydrocarbons. So it's obviously very difficult to do this in all places all of the time, but it leaves a significant legacy in how we're currently interacting with our places in the Midland Valley today. So geology has, I think it's the Midland Valley gives a really clear and stark example, both of how geology has informed how the place has developed in the past through the Industrial Revolution, population growth, but also how it continues to pervade how and where we build, live, and connect in the Midland Valley today. And just for the final bit of the talk, I just want to take this a little bit wider and look beyond the Midland Valley. And the second half of the chapter looks at the wider role of geology in developing places across Scotland, in thinking about how we develop climate resilient places, which is becoming ever more important as we live in a changing world. So the first of these I just want to touch on is infrastructure resilience. So this photograph was actually taken less than a year ago in Argyll on the west coast of Scotland, about a 40-minute drive from Oban. And as a result of this debris flow, luckily there was no loss of life or injury, just to reinforce that. But as a result of this debris flow, the communities along that coastline had a 4-hour travel time to get back to, their primary point of the next nearest town to do their shopping for about 4 months. So there's a huge community societal impact as well as an economic impact. So the sort of role and influence of geology in this: glacial erosion, steepened and lengthened slopes in upland areas of Scotland. And this has resulted in many slopes being left in an unstable state, particularly immediately after the glaciation and glacial retreat, resulting in a lot of mass movement, whether it was rockfall and rock slides or sediment-covered hillsides and debris flows. So we know that the majority of this mass movement occurs immediately after the glacial retreat, but it continues to a much smaller extent to the modern day, particularly debris flows. So although they're a lot less frequent than what they were immediately after the glaciation, they have a significant impact on our transport infrastructure, resilience, economy, and place. So events related to rainfall-induced slope activity, they have a significant impact on Scotland's road and rail networks. It's a real concern for Network Rail, Transport Scotland, etc. And it's often Rest and Be Thankful that gets captured in the news. Oh, Rest and Be Thankful's closed again. But, to give you an idea of the economic impact of that, it's 1.2 million for every 15-day closure. There's been a lot of closures over the last few years, and it's only increasing. But although Rest and Be Thankful is often the one which is captured in the media headlines, the image that I showed earlier, in which I'll just fast forward, this is the same, it's a bit of a grainy image, but it's the same debris flow and hill slope failure that I showed in the initial slide. It was a huge failure. And after that rainfall event, I think it was about 10 months ago now, in Argyll, there were several instances of similar debris flow scales to this, which weren't picked up in the media, but it had a massive impact on the area. Similarly with the rail network, Britain's rail network is still reported as being one of the safest, but the rail accident investigation branch reports are increasingly pointing to the fact to need to understand catchment scale processes and the influence of geology in informing how drainage is responding to rainfall and flooding. And this includes offshore debris flows. So this is an image in Holyloch of Western Scotland, and this part of the image here is actually underwater, but it's just picking up the survey results. And you can see this really clear slump failure feature here. Okay, so these have impacts to cable infrastructure, which often follows through these channels as well. So Scotland is going to see more increased intensity, heavy rainfall events. We need new infrastructure approaches which can be resilient to these in order to have connected climate resilient places. And geology, we need to understand the geology in order to do that. If you think beyond the Midland Valley, Scotland's a much larger place, and a lot of the energy and transport infrastructure passes through upland areas where this is all of a concern. Okay, and then just the final thing is water, particularly relevant today after the deluge of water that we've had today. But management of rainwater and surface water is long been an issue in Scotland. You know, our surface water drainage infrastructure was designed a long time ago, and rainfall patterns have changed significantly. We also have a lot more houses feeding into that same drainage infrastructure. SEPA, so the Scottish Environment Protection Agency, estimate that by 2080, the number of properties at flood risk will have increased to 270,000 in Scotland. And there are two ways which this is being explored to try to improve resilience, reduce surface water flooding. One is what's called sustainable drainage, and the other is natural flood risk management. And although they're all happening on the ground and above the ground, geology actually plays a really important part in them. So sustainable drainage, you might have seen some of these when you're out and about, these sort of vegetated verges and sort of drainage channels. They aim to kind of mimic natural drainage to attenuate and slow water going into the drainage infrastructure. But you can't put them anywhere. You need to inadvertently avoid the risk of groundwater flooding. If you're suddenly infiltrating water into a very shallow water table, it's just going to bring it up to the surface quicker. You also need to think about, is it going to lead to contaminants from road surfaces being then moved into the soil environment? And then finally, natural floodwater management. So this is looking at the catchment-wide approaches to try to reduce and slow movement of water through catchments. There's around 100 of these schemes in the UK, but actually we've yet to really understand if there's significant evidence for whether they're effective. So Graham might recognise this. So this is a picture of Eddleston, not too far from Edinburgh. So there has been a lot of research done in the Eddleston catchment around natural flood management. So here they've tried to do two things. One, they've tried to slow down the flow of water through the river by reintroducing meanders, as you can see here. So the river is now re-meandering, whereas previously it just used to go straight down here. And the other thing that's happened is there's been extensive tree planting. So I'm not meaning this forest in the background, but here on this hillside is now all completely covered in new trees of a variety of types. But actually the research that Leo had been doing as part of his PhD was showing that actually the effect of planting all these trees and the natural flood management approaches in Eddleston was actually much more limited compared to the role that the geology had in actually influencing how the catchment responded to rainfall events. So these are all within the Eddleston catchment, these graphs, but these two are from very similar parts of the catchment, similar geology, but one has a lot more tree coverage than the other. But the flow, the amount of volume of water coming through that catchment in response to a high rainfall event is very similar. Whereas in this one, where the geology was significantly different, but there wasn't actually that much tree cover, it was a much more subdued and controlled response. And these findings sort of correspond with work in other Scottish catchments, suggesting that the soils and the superficial deposits play a really fundamental role. So I think just to summarize, geology really needs to be considered in how we try to develop climate resilient places and place making as we look to the future so that we ensure communities are connected. So I'll leave it there, but just to summarize, hopefully the chapter sort of captures and illustrates some of the ways that geology has and continues to have a real role in how Scotland has developed and is developing as a nature, as a place. Yeah.